right. How's it going?
Excellent, Professor.
Right on. I'm doing all right. Everyone have a good first weekend. I guess it barely feels like Monday with the way time has been going. All right. Cool. The weekend is always shorter than people would have liked. Luckily next weekend. So it's next weekend is already a 3-day weekend. It's already 1 week from today is Labor Day, and we do not have class next Monday. I mean, you're welcome to try to connect to Zoom. I'm not going to be on, but so 3 days next weekend.
Not gonna lie, I thought that was this weekend, and I almost missed out on some of my classes.
Oh no. I think it is that the semester did start earlier this year, or maybe it's just that Labor Day is late. I think it's just that Labor Day is late. I definitely kind of had to like triple check my own calendar to make sure. Yes, I really am teaching today. Yes, I did write the class schedule correctly. Almost screwed up when I was making the syllabus and accidentally scheduled something for Veterans Day, but I noticed it, so we're good. No class on Veterans Day. Hopefully my email will not make a lot of noise in class. I did not turn it off, so. It just made noise. Hold on.
Hey, Professor.
Hello.
Yeah, I'm a new addition here for this class, and I'm like a week here, like two classes. I missed whole last week. So what's the progress and what I have been missing?
Actually, you're lucky that all of what we're doing is I've posted all of the lectures so far on a YouTube link at the top of our Canvas page. So you can actually watch what we did, but also if you look at our course Canvas page, we're going to be using that a whole lot. And so that's going to have all the assignments, all the readings, all of the, I post the slides after lecture, I post videos a couple of hours after lecture because they take a long time to upload. So everything is there, the syllabus is there. And so what I'd recommend that you do, anyone who's new, is just, first of all, just take a look at all that stuff and just kind of see what's there. And then just contact me, either email me, or like if you have any questions, just contact me, email me. You can come to my office hours on Tuesdays. If that's not a good time, then you can email me and we can set up another time. So anyone who added late, or just anyone who's confused about anything, even if you didn't add late, just at any time, feel free to reach out and let me know. But I really am going to post all of our class materials once we've gone over them in here. So those lecture videos are going to keep going up. Although I might actually shift them away from YouTube to another service, because apparently there's a more like education focused one that actually stays locked to your university and also has better closed captions. So I'll let you know if that switch happens. I'm still learning how to use it. But yeah, all the videos are going to go up after each lecture, and I'm going to post the slides after each topic. So far, I guess, yeah, it's two. So hello, everyone. Okay. Oh, someone, hold on. I got a message. So someone joined the Zoom call with a personal account. I thought it wasn't set to allow that. I might change the settings in the future to only allow people to log in with school accounts. But if you are logged in with a personal account now, that's fine. You don't have to leave. But yeah, basically, I'm going to post things as they happen. So for topics that are just one lecture, I'm going to post the slides after that one lecture. But we're going to have some topics coming up that are two lectures. And so I'll post the slides after the second one, but I'll still post the videos after each class. Does that sound good? Cool. All right, so we're gonna get started. Although before we do, again, don't forget that there's gonna be those little quick quizzes like pretty much every day. Not every day, every time we have a lecture. So there's not going to be one every day, but there will be 2 of them per week. They will always be due right at the moment class starts. So please get in the habit of checking Canvas and doing those. They're going to be 1 or 2 questions each. They'll literally take 2 to 3 minutes of your time. So the first one was due 2 minutes ago. And so I was not able to get, although I do accept late, it just loses 20% per day. So if you didn't do it, definitely do it. So I tried to get Canvas to do a thing where, so the way those are graded, that it's 2 points for a correct answer and 1 point even if it's an incorrect answer, just because you did it. Canvas doesn't do that automatically, so do not be alarmed if it shows a 0 for you right now. After class, I'm going to go through and fix those grades manually. So all of the quick quizzes, if you do them at all, you will get at least a point. But it doesn't do it automatically. I haven't figured out how to get it to do it automatically. So I am sorry if you saw a 0 and looked concerned. Do not worry. The second one of those quick quizzes will be due on Wednesday. So just kind of get in the habit of every day that we have a class, you're going to have 1 or 2 questions before that class to do. And also, the second of our little vocabulary matching things, because we're going to start talking about plate tectonics on Wednesday. The second vocabulary matching thing will be due then. And so those are not quizzes. You should use your books for those. You can do them as many times as you want until you get them right. The point of those is not to quiz you, it's to get you familiar with the words. And so Canvas calls those quizzes just because that's how you set up the assignments, but they're not quizzes. So any questions about that?
So, Professor, what should I do? I missed the 2 quizzes last week.
So how about, can you either hang out after class and we can talk about it then?
Okay. Okay.
Or you can email. But yeah, let's do that at the end. But yeah, I got you.
Okay.
So before we start today, I've got 1 more question. So there is a student in here who's registered with DRESS, which is the sort of the learning, the sort of disabilities and learning support center. And this student needs, they have an accommodation where they need someone to help them take notes. And so I was wondering if anyone in here would be willing to help share their notes with this other student. So if you were interested in helping with that, that would be awesome. It would be a big help, and both I and the student would be really, really grateful. So if that's something you'd be willing to do, just, you can take your notes as always, just be willing to share them. Please either email me or message me privately in the chat, and we can talk about that at the end. Yeah, so just please think about doing that. It would be really good of you. But yeah, so with those logistical things, does anyone have any other general questions before we, oh, this already switched slides. So I don't want it to be on that slide. Before we start with our topic today. Okay, cool. And if you do think of something, just say it or say it in the chat. So it says on our schedule that we're going to be talking about the structure of the Earth today. But in order to do that, we really need to talk about some basic chemical and physical processes and principles. Because we're not going to just, as I said, this isn't going to be just like memorizing how things are kind of class. It's going to be really learning about the processes that kind of explain why things are the way they are. And if you can remember the processes and remember why things do what they do, it's going to help you get a better sense of everything in this class and help you be able to put together the kinds of geological stories, the kind of Earth history that we're going to be getting at over the course of this semester. So if you remember last week, I mentioned that our definition of geology in here is the physics of the Earth and the chemistry of the Earth to tell the history of the Earth and how the Earth behaves now and will behave in the future. And so we need to go through some very, very simple chemical and physical processes to start getting at that. No math yet today. Eventually there will be some simple math in this class, so just you have been warned. But hopefully the stuff we're going to talk about now is something most of you have heard before in some other class, and it's hopefully going to be pretty straightforward, but if not, go ahead and ask. So spoiler slide, because this is what was up when I was talking. So gravity is in charge of very, very many things, and those things are not just falling. Gravity is so much more than just falling. Really, the effect of falling is actually that you, if you fall or whatever falls, is being pulled towards the center of the Earth. So really the definition of gravity we're going to be working with here, the real definition, it's this force that attracts things to each other. So as much as it just feels like falling when you fall, I said fall a lot in that sentence, you are actually being pulled towards the center of the Earth. And so it's a force of attraction. So if you have two equally large, equally dense things, they're going to act equal forces on each other. But in general, the bigger, denser, more powerful thing is going to have a much stronger gravitational pull on a smaller, lighter, less powerful thing. So like if you had, if you had 2 pounds of different things, like if you had a pound of iron and a pound of feathers, they would actually generally act pretty equally on each other, except for the fact that that pound of iron would depend on the shape it was in. Like if it was scattered over the same area as the feathers, you might have kind of equal stuff going on. But if you had a pound of iron in a very sort of discrete ball, that would, because it's denser, because it's more compact, it's going to have more of a pull on the pound of feathers. Or like if you have, a ball of iron and a ball of styrofoam, the iron is going to pull on the styrofoam more. But at the same time, if you had your little ball of iron and a really, really big, like a big enough ball of styrofoam that it weighed more than your ball of iron, the styrofoam would actually pull more. So it's just kind of the biggest, heaviest, densest thing wins. And hopefully that's all stuff you've heard before. It's just this sort of attraction, things acting on each other, but really it's generally a pretty straightforward thing. Like it's generally because gravity affects everything on Earth. I think a lot of the principles of this, like if you think about what would win in a fight, like a ball of iron or a ball of styrofoam, very often that same concept, if you were to anthropomorphize it, you can then step back and go, gravity's probably gonna work the same way. Heavier, denser stuff is gets sort of pulled in more and then has more of a pull. Does that make sense?
Yeah.
Awesome. And we're going to come back to that again and again. But yeah, that's how gravity works, especially for this context. Another very key principle is that heating something makes it spread out. So we're going to talk more about atoms when we talk about minerals, because you can't really talk about minerals without talking about their atomic structure. So starting in like 2 weeks, we're really going to get into some chemistry. But in general, if you heat something, its atoms spread out. So like if you think about water, if you think about H2O, so 2 hydrogens and an oxygen, if it's solid, it is an ice cube, and an ice cube takes up a certain amount of space. But then that liquid water, once you melt that ice cube, can spread out over a much larger space. It's not contained. Like in ice, those molecules are locked into a cube, and they stay there. They can't spread out. But when you melt that, the water's going to go wherever. And then lastly, when you evaporate that water into water vapor, into steam, it goes up and spreads out even more. So an ice cube might just sit on your table, but if you spill water, it's going to spill all over your table. And then if you evaporate it into water vapor, which would have probably happened just in the ambient temperature in Northridge last week, then that water is going to fill the entire room. So heating something makes it spread out. And that's true for everything. And in this class, we're going to be talking about solid rocks. We're going to talk about liquid rocks. There's going to be a little bit of rock gas. Not the main thing, but it's definitely something we're going to talk about. So just keep that in mind. Just a second. Okay. So any questions about that?
Yeah, I have a question. You mentioned rock vapor.
Um,
What is that?
so it's basically, technically by then it's not really rock anymore, because by definition, rocks are crystalline and they can't be when they're a vapor. But in certain, excuse me, in certain usually volcano-related situations, but sometimes much to the bottom of the ocean can also be a volcano-related situation. It can get hot enough that some of the atoms and elements in those rocks vaporize. And so like you can have, like sulfur can make rocks in and of itself, but you can also have sulfur gas, which is nasty. So things like that. It's just, you can get situations where it's hot enough that some stuff vaporizes. I mean, you aren't gonna be able to totally sublimate a rock from a solid into a gas, but some of the components in those rocks can become gas.
Thank you.
Right on. Volcanoes are wild. We'll get there soon. Any other questions about this one? All right. Moving on, if it lets me advance the slide. Similarly, working backwards, if you compress something, it heats up. And so if you have a bunch of stuff that's like, if you have a bunch of vapor that's just floating around the room, and generally, like if you have a vapor, the atoms are usually moving pretty quickly because they have a lot of room to move around. If it's in a solid, they're locked in place. But if you were to take all of that vapor and like shoot it into a space, like if you were to vacuum the water vapor out of the air into a vacuum chamber, then all of those atoms, even though they're still a vapor, are going to be closer together. And so you're going to have a lot of atoms like trying to move around all over the place in a small space, and that's going to generate heat. So like think about, for example, like let's say you are alone in your living space. I mean, it's hot because it's hot outside, but like you personally are not generating a lot of heat, right? But now let's say that it was sometime before 2020 and you had a lot of people in your house or in your apartment. Doesn't your place get warmer when there's more people in it?
Yes.
Yeah, so like people generate heat. All kinds of stuff generates heat. And so when you take a bunch of people and cram them into a smaller space, you suddenly have all of these things that are close, generating heat to begin with and are closer together. So the heat that was already there becomes it gets into a smaller space, right? And so that happens with people. It happens with or the same idea of like if anyone does compost, and you take all of your like coffee grounds or whatever, and your coffee grounds and your orange peels or whatever are not warm when they're sitting at the top of the compost bin. But if you were feeling bold and you stuck your arm into a compost pile, hopefully with gloves on, you would feel it's really warm in there, partly because you have compression of these materials and also because there's all kinds of biological stuff happening in there. But compressing stuff makes it heat up. And so things spread out you can heat things, and if they're hot enough and able to spread out, they will. But if they're not able to spread out, it's just going to keep adding heat to the situation. So a bunch of water vapor has to be a certain temperature, but it can be that temperature in the entire room. But as soon as you bring that vapor into a closed space, it gets warmer. And that's true for solids too. I'm using vapor as an example because it's already the warmest state of being. But the same thing is true with solids. Like if you have a rock that is just sitting there, it's going to be whatever temperature, room temperature is, right? But if you start squeezing that rock, I mean, a human isn't going to be strong enough to do this, but like there are machines that can squeeze rocks until they either break or heat up or start to flow. And so often this balance of pressure and heat, like heat makes things want to spread out, pressure keeps them from spreading out. And so you can have a balance of things want to be liquid or want to be gas because they're hot enough, but they can't be because they're compressed enough. So does that make sense?
Yes, sir.
So, and this is going to come up again and again and again. A lot of different things throughout geology have to do, especially with pressure. Heat is important too. I would say heat is very important, but pressure is probably even more important. But we'll get it, and that's going to come up again with all of the different kinds of rocks we're going to talk about. Then lastly, hopefully this one is also pretty intuitive. Heavier stuff sinks and lighter stuff floats. That's how it works. And that again is it's a very basic principle of like the rubber ducky floats in the bath, but if you drop a toy truck in the bath, it sinks. It's heavier, it's denser, it's made out of material that is less dense, that has more air, that has more space, is going to float. And actually rocks can contain a lot of air. The rocks on the surface of the earth in particular often include a lot of air. And so they're less dense, they're light. And so even though like granite is not going to float on water ever, in terms of rocks, granite is pretty light and it will float on other rocks. So a lot of the time when we're talking about things sinking and floating, like water has nothing to do with it. We're talking about rocks floating on other rocks. And so that is hopefully not too wacky of a concept. I mean, you can float things in syrup. You can float things in juice. You can float things in all kinds of stuff. So why not float a solid rock in a less solid rock? So that's kind of what we're talking about here. Any questions about that?
You mean they can float as in like the other rock is molten or something?
So sometimes, yes, but also sometimes you can get a situation where it just rises above the other. And so it's not necessarily floating like bobbing up and down in a liquid, but floating in that if you mixed the stuff together, the lighter stuff would end up at the top and the heavier stuff would end up at the bottom, just naturally. Does that make sense?
Yeah. Thank you.
So like if you mixed, again, water and syrup and you shook it up, at first it might just be a mishmash of stuff, but then if you let it sit, the syrup would sink to the bottom and the water would stay at the top. So
Yeah.
Whoops. So I feel like maybe I should have changed this to say rises rather than floats. But a lot of the times conceptualizing things as floating, even though it's kind of a solid rock on another solid rock, on a slightly softer solid rock, sometimes a lot of stuff still works well if you conceptualize it as floating. And so we'll talk about that a lot more next class when we get into plate tectonics, because actually this premise of light rock versus heavy rock drives so much of how the Earth moves and changes. So any questions on these basic premises, these basic physics and chemistry things? Cool.
Oh, sir.
Oh, yeah. Oh, no. Oh, that was a no. Okay, right on. And again, for people who are new, you don't need to like raise your hand or anything. Just it's okay to just talk. So far, people have not interrupted each other, so we're good. But yeah, then let's move on. So with these principles in mind, we're going to talk about the structure of the Earth. And these principles in different combinations are basically how the Earth got to be the structure that it is. But in order to get there, we're going to go back to the very beginning at first. So we're going to start with the Big Bang. Big artist's rendition, obviously. Potentially a questionable one because there's already stars in the background there, and the whole idea with the Big Bang is there was nothing and then there was everything. And stars took a while to coagulate too. But basically you had this big like infinite glob of matter that exploded and just shot atoms and particles and stuff through, well, it became the universe. And it's actually still getting bigger. But we're not going to really focus on the whole universe here. I just want to get at this to go like, where did all of this stuff that became the Earth come from? And it came from the Big Bang. But at the beginning, you pretty much only had like hydrogen and helium. So those are the two smallest elements on the periodic table, numbers 1 and 2, just itty bitty little atoms. But how did that turn into like things that are not gases? How did that turn into the vast variety of things that we have in the solar system and on Earth? And so the answer to that is even when you have a giant explosion that shoots things in every direction as the universe is rapidly exploding and expanding, stuff is still crashing into each other. So there's a lot of explosions and collisions in the early history of the Earth. And so this is a figure, this is in your book. It probably looks a little bit small on your screen, but this is in chapter 2 of your textbook. And so we're just going to sort of step through this. Basically, Big Bang happens. Lots of stuff is colliding. And eventually, as stuff is colliding, it sticks together. First of all, you get these small atoms crashing into each other and kind of sticking together and forming bigger atoms. So a lot of the different elements that make up the Earth and the universe happen from smaller atoms crashing into each other so hard that they stuck. But then that same idea of eventually you got not just atoms, but clumps of atoms, and then bigger clumps of atoms. And so eventually you had situations where there was something large enough to cause a gravitational field and pull in chunks of space dust. And so you would have situations where like you had a star in the middle, and stars are just rapidly combusting hydrogen and helium. So stars, including our sun, are mostly very light elements. But there's a lot of them. They're dense. They have a huge gravitational pull. And so they would pull in clouds of space dust, which would crash into each other more and get stuck together, just crashing and sticking and crashing and sticking until all of these things, you know, maybe first you had things like rings around the sun. So if you can imagine like the rings of Saturn, but rings of dust around the sun. And then eventually those things kind of turned into things like imagine a bunch of asteroid belts. And then eventually those asteroids crashed into each other enough that you started to get planets, which is just lots and lots of like interstellar pinball happening until you go from just hydrogen and helium, very little atoms, into big floating chunks of space rock orbiting combusting balls of gas. And so that's how pretty much every thing in the universe formed. It's sort of the larger versus smaller things are just kind of different stages of collision and sticking together. And also as things cool down, so things are cooling down after the Big Bang. As they cool down, like it's a lot harder, like if you have two, like say you have two molten marshmallows, it's very easy to just squish them together into this one larger marshmallow. Whereas if you have two marshmallows that are cold, you can like bounce them off each other, but they're not necessarily going to stick together. So over time, sticking together is less and less and less. But imagine a bunch of just really hot space rocks just globbing together. So eventually, these things started to be like asteroid or potato or whatever shaped. And then when these got big enough, gravity started to really come into play and started to really sort these things out into what is heavy, what is not. With the heavy stuff going into the middle, the light stuff coming out to the edges, and these things slowly just spinning themselves as they sort themselves until they became round. And so the roundness of the Earth, of the rest of the planets of the solar system, of all of the stars, comes from them being large enough to have gravity act on them and turn them into a sphere. And so that's why the Earth is round. It's kind of, this is where, this step 6 here is where we're going to go on the next slide. But in case you're curious about where the moon came from, another really big collision, another really big space rock hit the Earth as it was cooling and blasted more stuff back out into space. And so actually the Earth had a ring, kind of like Saturn, and then that ring kind of globbed itself back together into the moon. So the moon and the Earth actually, the Earth has more kinds of rock on it than the moon, but all of the kinds of rock that are on the moon also exist on the Earth. So just a little side fact about the moon. But does this general idea of stuff crashing into itself until it gets big enough make sense? The
Yeah.
early universe was really violent. But let's go back to step 6 here. So the proto-Earth, sort of proto being like pre, like the beta version of the Earth. The proto-Earth was molten. Everything in it was molten. So like imagine not a ball of rock, but like a ball of frickin' lava, like a sphere of lava hurtling through space around the sun. And so the process by which it became solid and layered is something we call the differentiation of the Earth. So basically it's that idea of, here's all this different stuff mixed together. We're going to make it not mixed together anymore. It's going to differentiate. And so early on, just a whole bunch of stuff was mixed up inside the Earth. It was hot. But then over time, first of all, gravity shoot all of this stuff together into ball. Remember what happens when you push stuff together, right? What does pressure do to things? Temperature-wise?
It heats it up.
Yeah, so exactly. So this is already really hot, but as it gets pulled together in a ball by gravity, it gets even hotter. And so in that case, like before, it might have just been the lighter weight rocks that were liquid, because lighter weight rocks melt at a lower temperature. We'll talk more about that in a few weeks. But at really high temperatures, it starts to melt metal. So there's a lot of iron in this. And then with that pressure, the iron got really hot and melted. And once it melted, it was a lot easier for it to move around. And so all of the really hot, the really heavy stuff, the metal, the iron and nickel, went sort of shoot then into the middle of the Earth. And so kind of, again, that idea of like, if this was the shaking up the syrup and the water together, then this is now the syrup goes to the bottom and the water goes to the top. So all of the heavy stuff went into the middle and the lighter stuff piled up on top of it. And so in general, the structure of our planet is the heavy stuff is in the middle, the light stuff is on the top. It's kind of floating. It's kind of just not floating. It depends on how you want to define it. But yeah, basically the center of the Earth is metal and the edges have relatively little metal. I mean, obviously not none. If there was none, it would have taken us a lot harder to like have the Bronze Age and stuff. But for all of the metal that there is on the surface, there's way, 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 way more in the center. But yeah, and then as this got there, it was a situation where, yeah, it heats up more, but there's also so much more pressure because now that this is really, really dense, it's not just sort of stuff of mixed density acting on stuff with mixed density. You have all of this really dense, heavy stuff squeezing itself. And so it started to become an interplay of like, is it hot? It's hot enough to be liquid, but it's also squeezed enough that it kind of can't be liquid. There isn't room for it to be liquid. And so these kind of processes, this separation of what's dense, what's not, what's hot, what's not, what has room to be liquid, what has not enough room and stays solid. Sort of these interplays between all of those laws that we talked about, all of those physical and chemical properties that we talked about at the beginning, led to the Earth being a mostly solid ball of rock and metal, and eventually turning into what we have now. So does that make sense? And this was a long time.
Yes, sir.
Yeah, so this is all at the this started at that 4.6 billion years ago mark, and definitely took millions of years before things were solid enough for anything else to start happening, like hundreds of millions of years. So, got an Earth and it has layers. And now technically, if you're getting into Earth science, like Earth system science, so in this class, again, we really are focusing on the solid physical planet itself. But there are actually layers above the rocks. So the rocks, the planet that we're walking on is the geosphere. But above it, you can have the hydrosphere, which is water, which is less dense than rock. So it sits above the rock. The cryosphere, which is ice. So if you think about like cryogenetically storing Captain America, cryo is ice. Ice is less dense than water, so it floats. Biosphere is living stuff. We're going to touch on this a little bit in this class, but obviously this can't, there's some biosphere at the bottom of the cryosphere and the hydrosphere, but mostly this stuff has to exist on the top or it's going to get crushed. And then lastly, the atmosphere is gas. Gas is the least dense. So all of this is still held onto the planet by gravity, but it goes from the most dense up to the least dense. So that layering wasn't just the solids, it was the liquids and the gases too. And so the outer edges of our atmosphere kind of mark the outer edges where the gravitational center of the Earth can hold on to those gases. But yeah, atmospheric science is a whole other thing. We're not really going to talk about this that much. Biology, biosphere is biology. We're going to touch on it a little bit with some kinds of rocks, but not a whole lot. Yeah, this class is really, we're going to talk about the geosphere. We are really going to be focusing on understanding the densest, lowest layer and the layers within it. But yeah, we're going to, you can't talk about certain kinds of rocks without talking about water and without talking about ice. And so we will be talking about rivers and floods. We'll be talking a little bit about glaciers, because glaciers you don't mess with water. You don't mess with ice. Ice will beat rocks every time. But we're really going to be focused on the geosphere. So even though there's all of these layers, and I guess I'd like you to be aware of what these 5 layers are. Like if I ask you, what's the cryosphere? I'd like you to know that that's ice. But really the majority of this class, all of the details we're really going to get into are geosphere details. And so when I say the layers of the Earth, like on the study guide that I posted on Canvas, for example, we're really going to be talking about the layers of the geosphere, because you can subdivide and subdivide and subdivide. Actually, last class, when we were talking about understanding layers to understand the history of the Earth, that was actually just the layers of the top of the geosphere. So there's layers within layers within layers within layers. There's a lot of stuff to think about. But here, again, geosphere is where we're going to be hanging out. It's also literally where we live, is on top of the geosphere. But we're going to be hanging out in geosphere land for the majority of this semester. And actually surprisingly few things make up the geosphere. And so these are the elements that make up the Earth, that make up all of the solids of the Earth. And we'll talk, don't worry too much about this yet. This is going to come back again and again and again. So I'm just giving this to you now so you see it first. It's going to come back for plate tectonics. It's going to come back for minerals. It's going to come back for like everything. But there are surprisingly few elements that make up most of the Earth. Iron makes up a lot, then oxygen, silicon, magnesium. And the majority of the Earth is just these 4 elements in different combinations to make different molecules, to make different minerals, to make different rocks. And then like you've got another 4, then nickel, sulfur, calcium, and aluminum are another decent sized chunk together. And then everything else, like there's 100 and something teen elements on the periodic table now. The others make up less than 1% of the planet. So when we're talking about the chemistry of rocks, there's really basically 8 elements that we're going to have to worry about, but especially, really it's mostly 4. Most of what we're going to get into, like with volcanoes, it's really just these 4. with sedimentary rocks, some of these others come into play, but 4 elements. And so in the context of the structure of the Earth, in the context of less dense versus more dense, less heavy versus more heavy, light and fluffy versus dense and not fluffy, it's this balance between things that have a lot of silicon and oxygen versus things that have a lot of iron and magnesium. So if we something that has a lot of silicon and oxygen, we call that silicic. Don't worry about that word yet. You'll get that word later. Or silicon rich. And then magnesium and iron is metallic. It's metal. So it's kind of the balance of this stuff, these two, floating up higher, rising up higher because they're light. And magnesium and iron dropping down and being heavier because they're metal. Metal's heavy. And then all of these others, most of these others tend to mix in more with the silicon and oxygen than with the magnesium and iron. But any questions about this? And you will see this chart several other times in this class. And so I'm definitely not going to ask you to memorize this. I'm never going to ask you, like, what are the percentages? But it would be useful to know, like, which 4 elements make up most of everything on Earth, for example. But it'll come back. So yeah, and so this chart, and especially this balance of silicon and oxygen versus iron and magnesium, really controls the structure of the Earth. So now let me ask you, I don't know what grades they teach Earth science in anymore. I've mentioned it in high school, but then someone else in here, like on their my sort of tell me about yourself survey, said that they didn't have geology in high school, which, yikes, that's not cool. But anyway, in whatever grade you last took geology or earth science or whatever they called it, what did they teach you about the layers of the Earth?
The last time I took a geology class, I think, was in 6th grade.
Ooh.
So it's been a minute, and just like the crust, the mantle, the outer core, and the inner core, like that's all I remember.
Yeah, so does that is exactly the answer I was expecting. So right on. I'm alarmed that it's 6th grade. Definitely alarmed about the 6th grade aspect. But definitely that's the very common thing that they teach people, and that is totally a valid actual way that we describe the Earth. That is very much a scientific way to do it. But there are actually 2 ways to describe the layers of the Earth. And so in here, we're going to talk about both of them. So that crust, mantle, core distinction, it's the simpler one, which is probably why they teach it in elementary school, or why Bill Nye the Science Guy had songs about this one and not the other one, is that it is a simpler. There are fewer layers. But basically, there's the more technical way to describe this is the chemical or compositional way to describe the layers of the Earth. So the distinction between crust, mantle, and core is what is in it. Like, what kind of stuff is there? Is it more oxygen and silicon, or is it more metal? And so it's really just a layering by density. So actually, this chart, which is in this chart is from a different textbook. There's a very similar one in your textbook, but I like this one better. But I wasn't going to make you pay for the more expensive textbook just to have a nicer chart. This will be on Canvas. You notice that this actually lists some densities going down the center line here, saying that, you know, stuff that's on an ocean or a continent is not super dense, whereas stuff that is in the core might be 16 times as dense as the stuff on the surface. So this is just what's in it. How dense is it? But the other way to think about things on the left is what we call the physical or mechanical layering of the Earth. And so both of these are equally correct. They're just different ways to think about what's going on. So if on the right is what is it made out of, on the left is what does it do? How is that rock moving and changing? How is it deforming or not deforming? What is happening? What are its physical properties? So crust, mantle, core is thinking about it in terms of chemistry. And then on the left, lithosphere, asthenosphere, mesosphere, outer core, inner core is thinking about it in terms of physics. So the physics version of what the Earth is structured like and the chemistry version of what the Earth is structured like. And so really these things inform each other. Like definitely some things about the chemistry inform how the physics work. Like certain chemically, like metals are going to behave in certain ways physically. Rocks with a lot of silicon in them are going to behave in certain ways physically. And certainly the physics can actually affect what the chemistry is doing, as we'll talk about when we talk about metamorphic rocks. Metamorphic rocks are all about physics messing with chemistry. So these are related, but also separate ways of thinking of things. And so what we're going to do for the rest of today is just talk about these two different ways of thinking about it. And I would like you to know the names of all of these layers. So we're going to go through each one on its own slide. But it says on your study guide, like, know the layers. So please know the layers. But any general questions about this before I go on?
Professor?
Yeah.
So you said there was a compositional way and a physical and mechanical way.
Yes.
And is it correct that the compositional way you would say the crust, mantle, and core, and then the physical and mechanical way you would say atmosphere, hydrosphere, and like lithosphere and stuff like that?
Absolutely. 100%.
Thank you.
Again, we're not going to really worry about the atmosphere and hydrosphere in here. We're not going to talk about them today, but they still behave in different ways. Like liquid water behaves in a certain way. Gaseous oxygen behaves in a certain way. So it's still, they're related. Like certain chemistry and certain physics inform each other. But yeah, exactly right. Cool. So going to move on. So we're going to start with your the way that is most commonly taught in schools before college. And so that chemical or compositional layering. So you're describing the Earth by its chemistry. It's defined by what is in each layer. And it goes from less metal at the surface, so lots of silicon and oxygen at the surface, down to pure metal in the middle. Less dense to more dense. Pretty straightforward. So I'm not going to ask you to know these density numbers. Definitely knowing, you might notice that this says the continent has a different density than the ocean. Actually, that got that backwards. That's the wrong numbers. The continents are less dense than the ocean floor. That's, we'll talk more about that next time. But you don't need to know these specific numbers. Just which is more dense, which is less dense. Any questions about that? Cool. So we're going to start with the crust. Oh, yeah. Question? Okay. Okay, we're going to start with the crust. This is where we live. Everything that we interact with and see is the crust. Humans have not gone into something that is not the crust. It is way down there. So everything, mountains, valleys, the beach, the desert, everything you're going to see is the crust. Every rock that you're going to pick up, almost every rock. There are some cases where mantle rocks can get up, but pretty much every rock you're going to see, whether it's granite, whether it's sandstone, whether it's volcanic rock, whether it's weird rocks that are shucked up out of the ocean. All of those are crust. Any rock that you're going to easily be able to find and touch is the crust. And actually, pretty much everything we're going to talk about in this class is the crust. And then part of that is that's what we can see. Like, geologists in the 1800s were not really actually even terribly aware of the mantle at that point. But definitely, they weren't digging down deep enough to see the mantle. But also, really, because the Earth kind of congealed into this layered structure pretty early in its history, pretty much all of the action, all of the really big change is on the outside. Definitely things are moving around and changing on the inside, But the crust is the most actively variable. But also it's just what we can see, the geology of what we can see. But yeah, from a compositional standpoint, it's low density light rock. So you got a lot of silicon and a lot of oxygen in that rock structure. And we'll talk about that a lot more when we talk about minerals in like 2 weeks. But basically, this oxygen, by the way, is part of a solid structure. So you can have oxygen atoms in a solid rock structure. You can also have rocks that trap oxygen gas in them, but in this case, they're actually in the rigid chemical structure of the rocks. A lot of oxygen, a lot of silicon. Just in the grand scheme of rocks, what you're going to find on a continent is light and fluffy. It is the marshmallow whip of rocks floating on the very surface of the earth. And by the way, a lot of geologists really like food analogies. If you get more interested in geology, and especially in tectonics, in how landscapes and move and change over millions of years, people use so many food analogies. There's creme brulee versus jelly sandwich versus a lot of food analogies. But yeah, most of the stuff like, you've got your, the light and the continents are the light and fluffy rocks of the earth. And it's that silicon and oxygen that make them light and fluffy. So if you were to take a chunk of continental rock from the crust and a chunk of mantle rock that were the same size, that mantle rock is going to be like so much heavier. Because if it weren't, it wouldn't be in the mantle. It would have floated up to the crust. Like by definition, it has to be lighter to be in the crust. Does that make sense? Cool. I see thumbs ups. Cool. All right. So moving down, the mantle is not molten lava. That is a very, very common misconception that a lot of books like to say. A lot of who has heard that the mantle of the earth is made of molten lava? I see many. I'm scrolling through, see a lot of hands up, or I see an applause emoji. Yeah. A lot of things say that the earth is not, the mantle is not molten lava. Actually, most of the time when you get molten lava, it's actually a small amount of molten rock. And it's just it's usually hanging out in the crust or kind of between the crust and the mantle. But the mantle is still solid rock. It is very hot solid rock, but it is solid rock. And it has a lot more metal in it. And so in that case, you still have some silicon and some oxygen, which is why it's above the core. But there's also a lot of metal in it, so it's below the crust. It's a mix of these things. And actually, a lot of the mantle is green. But a lot of books will draw it either as just some brown rock color, or some of them draw it as orange. Like this picture that I have on my Zoom background has the mantle as it looks like molten rock. Is not. I mean, it's definitely really stinking hot. It is actually probably hotter than lava. But because of the pressure, it's still solid. But yeah, a lot of mantle rock is green just because the kind of minerals that form when you have this combination of silicon, oxygen, and metal, it just makes this rock that's green. So if you've ever heard of olivine or peridot, like the gemstone peridot, is this green mantle mineral. Pretty cool. If we were in person, I would be handing you a chunk of this. We know what this looks like because there are some cases where you have really hot volcanoes that just kind of drag this stuff up out of the mantle. And so there are places in Hawaii where you can just go and pick up chunks of the mantle. And so if we were in person, I'd be handing you a chunk of the mantle right now. But and you would notice that it's heavy. These things are heavy. Definitely when I flew back from Hawaii, airport security was like, what's going on, dude? Came back with a lot of rocks. But anyway, generally at any time, I have had airport security ask me, what do you got in there, rocks? And the answer has been yes, and they've been like, okay. But anyway, I digress. The mantle is dark colored rock that is heavy. It's going to be usually green or black. Mix of metal and silicon and oxygen. And it is not molten and it is not lava. Any questions about that? Cool. And moving down, The core is metal. It's just metal. That's what it is. It's iron, it's nickel, it's magnesium. It is solid. Well, some of it's solid, some of it's not, but that's actually kind of the next, that's the physical one. The core is just a big old chunk of iron and nickel. That's what it is. Very heavy, very dense. This picture is not a piece of the core. This is actually a meteorite. But if you think about, the Earth forming as a bunch of space rocks crashing into each other, some of which were metal, in a way, the stuff that eventually became the core was pieces of rock like this, crashing into each other and then melting and then gravity pulling them to the center of the Earth. So even though this flew in from space, if you were to take a chunk of the core, which no one has ever done, there is no volcano hot enough to have dredged up a chunk of the core from like 3,000 kilometers deep. None of this is on the surface of the Earth, but it's the same general idea as this meteor. So just think of, it's heavy metal. That's what it is. Very straightforward. Any questions about that? Cool. So in general, this chemical description of the Earth is the simpler one, because it's just what is in it. But how does it move is a more complicated question. So we're going to move on to the physical or mechanical. And I think your book uses this interchangeably, physical and mechanical, and chemical and compositional it also uses interchangeably. So whichever, both of those are right. If you remember one and not the other, that's fine in terms of the name. But yeah, the physical and mechanical layers are more complex because it's this description with physics. It's not just what's in it, it's how is it moving. And in general, how it moves is a combination of, well, that's a typo, of how hot things are. Now, not how things are. I'll change that before I upload it to Canvas. It's a combination of how hot things are and how much pressure they're under. So it's a balance of like, is it hot enough to be a liquid or a gas, but is it compressed enough to keep it solid anyway? Is there enough room for it to become a liquid or gas despite its temperature? So none of this is gas. Well, the atmosphere is gas, but we're not going to talk about the atmosphere. We're going to talk about the lithosphere, asthenosphere, mesosphere, outer and inner cores. And so those really are like, how hot is it, and how much pressure is it under? So any questions with that before I go on? Okay, so the lithosphere is pretty analogous with the crust, actually. So the lithosphere is where we are. It's the outer layer. Lithos means rock. It is the rock sphere, except honestly, these are kind of almost all rock. But lithosphere is the rock that you see. It's the surface of the Earth. But in this case, rather than describing it as being the rocks that are light and fluffy enough to be at the top, we describe them as they're cold, they're solid, they're brittle. So this rock breaks. I mean, in general, when you think about like hitting a rock with something, you're not going to ever think about a rock flowing, right? Like, have any of you thought about rocks that are solid flowing before? I see some shaking heads.
No.
Yeah. So it's kind of a weird concept, right? That something that's solid can flow. There actually are examples of that. We'll get to that. But in generally, lithosphere is rock that breaks. It's cold and brittle. If you whack it with something, it's going to shatter rather than flowing out of the way. And as such, when it moves around in discrete chunks. It moves around in plates. So there's a reason I have a picture of a broken plate here, is this is the basis for plate tectonics. It is the discrete chunks of the Earth's lithosphere, these solid brittle chunks that are separate, moving around and hitting each other, or moving away from each other and hitting each other on the other side. It is, so the lithosphere, even though it says solid here in the context of it being solid rock, but it's actually broken up into a whole lot of little sections. And the reason they're moving around is not that they're moving because of themselves. They're not under enough pressure to be particularly hot. And so they're solid. They're not flowing. The reason they're moving is that the stuff below them is moving. So in terms of thinking about the physics of how the Earth moves, it actually, even though we're going from the top down and describing these layers, it really works from the inside out in terms of why things are moving. So we're going to go from the top down and then kind of describe it from the bottom out at the end. So any questions about the lithosphere? Again, I'm not going to ask you what lithos means, but remembering that it means rocks is probably going to help. So moving down one. So the asthenosphere is the layer below the lithosphere. So in terms of the chemical model, this kind of correlates with the lower part of the crust and the top of the mantle. So the chemistry in here is kind of mixed. But from a physics standpoint, this stuff is still solid. It is solid rock. But because it's warm, it sort of behaves like soft plastic. So it is not literally plastic, which you notice this is in quotation marks. It is not literally made of plastic. It is made of rock. But that rock kind of is analogous to like silly putty. Like there are certain cases where you can actually break silly putty. There are certain cases where silly putty flows. Like if you notice, if you like stretch it out, it's going to stretch pretty far because it flows. But if you have like a chunk of it and just go, you can still snap the silly putty. So the asthenosphere, you kind of imagine it being analogous to that. It's actually way harder than silly putty. It's not literally this squishy, but it's a similar premise. So it's warm enough to flow and deform, but not actually warm enough to melt. So it's also under enough pressure that it doesn't melt. So actually the reason that you tend to get liquid rock kind of at the boundary of the asthenosphere and the lithosphere is because there it is warm enough to melt, but is not under enough pressure to keep it solid. So here, it's warm enough that if it were not under pressure, it would melt, but it is under pressure, so it doesn't melt. So the asthenosphere is very slowly flowing over time. The name asthenosphere refers to the fact that it's kind of plastic and flowy and squishy. And so it just is very slowly moving over time. And so the tectonic plates of the lithosphere kind of imagine like if you had like a dinner plate and you put it on a bunch of silly putty, you would be able to kind of slide that plate around on the silly putty. The silly putty would allow it to move. So hold on, I see, oh wait, no, that no on there was referring to the solid rock flowing, right? Sorry, I just saw that, Jade. Anyway, yes, so this is solid rock and it flows. And it flows pretty quickly, and it doesn't break. And the lithosphere moves around on top of it. Another way to think of it be like kind of like the ball bearings below the plates of the lithosphere. Does that all make sense? Any asthenosphere questions? Then let's move down one. So the mesosphere, meso means middle. It's the middle layer. It's the third out of fifth. And so mesosphere, all of the rock in the mesosphere correlates with mantle rock. So if you're lining up those two things. And so this is another case where it's still solid. It's still solid. It's hot enough that it can flow, but it's compressed enough that it can't flow very much. And so in this case, because it's deeper in the earth, it's under more pressure than the asthenosphere. So rather than behaving like silly putty, like sort of weak, flowy plastic, it behaves more like a stiff plastic. So here I got a picture of a water bottle. Like I'm sure many of you are familiar with these things that like seem like they're really solid. I mean, they are solid. They're kind of unbreakable water bottles. But like, let's say that you let's say you set that water bottle down on your desk and didn't move it for 100 years. If you were to look at it then, if you were to analyze the thickness, it wouldn't have melted into a puddle or anything. But if you were to come back to look at that water bottle in 100 years, or especially in like 1,000 years, and then you were to measure the thickness of the plastic at the top versus the thickness of the plastic down here, you would find that it actually is thicker down at the bottom, because over time that plastic is flowing very slowly, too slowly to see. So like the silly putty, you can kind of notice it. This plastic, not so much. But over time, it is flowing. And actually, glass does that too. So even though glass is a solid, it does flow very slowly. So like if you ever get a chance to visit, like if you ever get a chance to go to, say, Europe and see some, 1,000-year-old cathedral with stained glass windows, or just with big windows, you might notice that like the glass at the top of the windows is going to look a lot thinner than the glass at the bottom of the windows, because the glass is slowly flowing. And so like Europe is a good place to see that, because you've got a lot of really old glass windows. You don't have too many earthquakes in Europe to break your glass windows, so they've had some pretty old ones. So the mesosphere is kind of like that. So it's like stiff plastic, and it is convecting slowly. So who knows what convection is? Okay. So we will talk more about convection when we talk about plate tectonics. But basically convection is boiling, basically. It's that idea of hot stuff rises, and then it kind of stays at the top and loses heat because it's away from the heat source, and then it sinks back down towards the heat source. Yeah, hot goes up, cold goes down, exactly. But it's a cycle of hot going up and cold going down, so that's exactly right on, Mario. And so it happens over and over and over in what we call a convection cell. And so in the mesosphere, there's actually a bunch of convection cells of places going in these hot and cold, hot rising, cold sinking, hot rising, cold sinking, all throughout the mesosphere. And so it's going pretty slowly, but it's happening. This is a process that it's not like boiling water where it's going super fast. It can take millions of years for one bubble. It's not literally a bubble, but one convection cycle to happen in the mesosphere. But that convection in the mesosphere is kind of what makes the asthenosphere kind of flow. And then because the asthenosphere is flowing on top of those convection cells, the plates of the lithosphere are moving too. Does that make sense? But then you might ask, why is the mesosphere convecting? Because there's a heat source below it. And that heat source below it is especially the outer core. So the outer core is liquid. There is liquid inside the Earth, but it is not the liquid lava of the inner mantle. No. Also, by the way, something to be defined as lava, it actually has to be out on the surface. So even if the mantle were liquid rock, it would be magma and not lava, but it isn't. But the outer core is liquid. It is liquid metal. It is boiling really rapidly, liquid metal. So in this case, even though there's a ton of pressure in there, there's a whole lot of pressure in the outer core, it is just so hot that the heat still allows that metal to be liquid. In this case, heat wins over pressure. So pressure keeps it contained in the outer core, and gravity keeps it contained in the outer core. But it's so hot that it is just boiling metal. And so this is boiling water. I couldn't really find a good picture of boiling metal because it's kind of hard to get metal that hot on the surface because the air cools it down so immediately. But in here, it's confined. And so you've got just rapidly convecting liquid metal. And so in this case, you have this rapid convection, that the hotter metal getting heated from inside and going up, and then getting less hot and going back down very quickly in the outer core, which then provides the heat source for the mesosphere to convect more slowly, which then heats the asthenosphere and makes it move around and then drags around the lithospheric plates. This is, I guess, sort of turning into like a 12 Days of Christmas kind of situation, but you get what I'm saying? So yeah, there is a vat of boiling liquid metal inside the planet, which is kind of metal as hell, really. Any questions about that? Cool. So the last layer, oh yeah, cool. So last layer inside is the inner core, and it is solid. So the inner core is the hottest. It is hotter than the outer core. But because it is the very center of the Earth, because literally everything else on Earth is confining it, because gravity is acting on all of these other layers to compress the inner core, it is so hot, but it is also so confined that that confinement keeps it solid. So it's not really moving inside of itself. So the whole planet is rotating. We're really not actually going to talk about the rotation of the Earth that much in this class, but if you remember, the entire planet is rotating. Weirdly, the inner core rotates the other way, which is weird. It's poorly understood why that happens. But it's still behaving as a unit, is behaving as one very large ball of extremely hot solid metal. But basically, this is the heat source. It's so hot that that heat kind of drives everything else. So, inner core, really hot, heats the outer core, which has not enough pressure to stay solid, so it convects, which then heats the mesosphere, which is confined enough to stay solid, but it still boils and flows, which then heats the asthenosphere and makes it really soft and flowy, which allows the lithospheric plates to move around on top, and a partridge in a pear tree. Does this make sense? So you can see why this one is more complicated, right? This is one they don't teach it in elementary school so much because there's a lot going on here. But the idea of heavy stuff sinking and light stuff floating is you get that from your first experiment, just being a baby and dropping things in water even though your parents told you not to. So when we talk about plate tectonics, we're really going to be dealing with this system, with this physical, mechanical thing, because the plate tectonics is the physics of the Earth. It's the physics of how the Earth is moving and changing. It's the physics building blocks of the Earth, like this is. Whereas when we talk about minerals, that goes back much more to the chemical or compositional structure of the Earth. And so that's kind of why I've lumped plate tectonics and minerals and the structure of the Earth into the content of our first test. Because even though like plate tectonics and minerals might seem like two super different things, they're just the physics way of thinking about the Earth versus the chemistry way of thinking about the Earth. And so that's why those are going to go together on our first test. Before I go on, so one other thing to think about that's pretty cool and also pretty important for how we discovered plate tectonics is that the Earth is actually a magnet. Because there's a ton of metal in there. So iron is magnetic, nickel is magnetic. There's a bunch of magnetic stuff inside the Earth. But because the outer core is flowing, because you have a bunch of metal boiling and moving around, it generates a current, generates an electrical current or a magnetic current as these particles of magnetic stuff are rapidly flowing around. And so the Earth is magnetic. And the thing that's, I don't know why I guess just because a lot of, come back. A lot of thinking is Eurocentric, and so they decided that Europe was up as opposed to Australia being up. So I guess with that Eurocentric thinking, the North Pole is next to Europe and the South Pole is opposite of Europe. But from a magnetic standpoint, from a standpoint of magnetic north, the South Pole is magnetic north and the North Pole is magnetic south. That's the way it is right now. But as it turns out, because the stuff in the outer core is flowing, sometimes the magnetic field of the Earth flips. Sometimes magnetic north and geographic north are the same, and sometimes they're not. And so far as we can tell, we have no idea why it switches, but it does. And so if any of you have seen the movie The Core, which is an absolutely terrible movie with no real science in it, but it's It's pretty fun. It's like so bad that I enjoy it. The whole premise of that movie is that the core stops spinning. I love that movie, that Zachary. I love that trashy movie with all of my heart. Many geologists love that trashy movie with all of our hearts. It is so bad, but a few years ago at the American Geophysical Union meeting, they actually had a session about movies and geology, and they brought all of these filmmakers to a geology conference, and they had I forget if it was the director or the screenwriter of The Core agreed to be in this room with a bunch of geologists grilling them. It was great. It was great. A lot of it was actually like, it wasn't attacks. It was just like, why did you choose to do this? But when you think about it in this case, like, yeah, it's kind of wild that the Earth's core is moving and is causing the magnetic fields to flip up and down and go bonkers. And so that idea of like, what if that stopped and the magnetic field didn't just flip, it went away? You can kind of see where they're going with making that into a really terrible disaster movie. But so long as the Earth's core is the outer core is boiling, and it's going to keep boiling because of that balance of heat and pressure, that's not going to stop unless something makes the entire heat of the Earth go dead, in which case we'd have a lot of other bigger problems like gravity probably stopping too. It's not going to stop. That movie can't happen. But again, that idea of boiling metal generating a magnetic current, it sometimes switches which way is north and which way is south. As it turns out, if there's metal in your rock, then the metal in that rock is gonna, as the rock is cooling or as the rock is turning into a rock, is gonna line up with whichever direction is magnetic north. And so sometimes that's a way if you can differentiate which rocks formed when by going, oh wow, you have some granite next to some other granite and they look kind of the same, but in some of this granite, the metal is pointing one way and some of it's pointing the other way. That lets you know that there was a change, that something happened. And so the direction of magnetic particles in rocks is actually another way you can tell the story of how things formed and when things formed. And as it turns out, the magnetic field was key for knowing how plate tectonics happens. So with that, are there any questions about that? Any questions about literally anything else? Then that said, that's it for today. So we're a few minutes early. So there is another quick quiz that will be up right after I end this class. And then there's going to be more vocabulary matching for plate tectonics for Wednesday. But then after that, there's not going to be another vocab matching for a few days because Monday is Labor Day. Next Wednesday is still plate tectonics. So so with that, if you've got more questions, feel free to hang around. I'll leave the Zoom meeting up. But if not, I will see you Wednesday.
Sir.
Yeah.
Now I'm the student who missed 2 classes before this class. And what about 2 quizzes? I saw in the canvas we can take, but if I take today, all the quizzes would be late submitted.
I will open them back up for you. Because you added late, I will make them due at the end of this week.
No, okay? the quiz is open, but I think there would be mark of late submission. So
no,
just see about
I can change
that.
I have the power. I can change them. They won't be late for you.
Oh,
yeah.
Thank
so
you, sir.
I'll change your deadline to Friday. Is that okay?
Okay, thank you, sir.
Right on. Then, yeah, and feel free to let me know if you have any more questions. And the other lectures are up on that YouTube link.
Yes,
so the vocabulary is due Wednesday before class or after class?
It's due before class because part of the point of that is it exposes you to those words one time before we do them in here. So it's just the more times you hear a word, the easier it is to get used to using it and understanding it. So just by looking up those words before class, they aren't going to be like a totally alien to you by the time we start class. But there's only a few of them. It shouldn't, and for the most part, I use the wording that is in the book, except in some places where I don't like the wording in the book, but it's still similar. So does that make sense?
Yeah, thank you so much.
No problem. I'm talking with Halia in text, but does anyone else, do either of you two who are still in here, Jade and Trinity, do you have any questions? All right, then I'm gonna close the session. Halia, I will email you. Thank you again, and I will see you all on Wednesday.